So this is my review of lecture 15, projections onto subspaces. So first let's discuss about the first point. Let's do it on the one-dimensional subspaces. So here I get the subspace of A, which is just a line 1D, and I have another vector B here, which is clearly not in the subspace of A, and our initial goal is to find this equation right here. So ax equal b, so I want to find the solution of x that will bring me from A to that satisfy this equation. But clearly, as you can see here, there is no a combination of the column space in A that equal to b, again because this x is actually just a combination of the column inside A. That's what we learned from the early in the lecture. So we cannot find this one. So what we want to find instead is this. How about if we find the nearest projections of B? So we name it P, and then we find this equation. We want to find the x hat. So this term x hat means we no longer care about the initial x because this can't be solved. So instead we are interested in this one. So the nearest projections is always the one with the right angle. So imagine that if I have a flashlight here and then there's a light there, and this will create this projection. So it will shine on here, and then the projections will be kind of like this, P. But we can also have the flashlight sits upright above the vector, and this will create this blue line projection of P. So the nearest projection is always form that right angle, and this is where what we learned from lecture 14 will come into play. So we know from the previous chapter that those the vector that are orthogonal equal to 0. So let's write there. So I'm going to write A and E as orthogonal. So this is the dot, which is also equal to this one. So that's equal to 0. And then let's expand E. So what is E? E is equal to B minus B. And where I got this is actually pretty simple. So B equal to the vector P times E. So E is B minus B. Okay. Now let's continue from here. Now I will expand P. So what is P actually? Again, P is a combination of columns of A. And here we use the term x hat because it's no longer the initial x. This is another set of x that creates this projections vector inside those subspaces of A. So let's continue it here. So we expand it, and then AP equals 0, AP equal to AP, and AB equal to A times x hat. So we got this A dot B over A dot A equal to x hat. Okay. Or in the lecture, Professor Shrang wrote it as the transpose B over A transpose A. So we got the x hat, our solution. And another thing that we're interested in, of course, we want to get the projection speed. So if we write this one again, let's rewrite those things. We will get this that's my mistake, A. Okay, so we now have our projections for vector which equal to A x hat, and then we expand x hat into this one. And there is another thing that we're interested on is the capital P in the lecture itself. So this is the projection matrix. So if we were to project the vector b into the subspace of A, in the end we just transform b into the p. So there must be a matrix that acts on b. So we name it the capital P b equal to the projections and our final projections. And what is the b? And it is clearly is here. So if we just play around with the parentheses, so this is will be our big P. Okay, so those are the three things that is really important. That is will come into a more important role in the higher n dimensional. So this P, I'm sorry, so this P right here, and then lastly is this, let me rewrite those. So P, the big P equal to A transpose times A transpose A. Cool. Now that covers the first point, so let me just quickly also discuss the two important properties of this matrix P. Let me write that. So matrix P, which is the capital P, so it is symmetric, and if we do the projections on it, it will equal to the initial projection. So that means that, in a word, that if I already got P, like, okay, first of all I project B to get P, and then if I again project P with the same matrix, that it won't change my projections P. So that's why the square of P will be equal to P. So let's prove that quickly. So we have P here. First I want to prove that the capital P is symmetric. So like get here, and then let's transpose this one real quick. And remember the transpose rule, that the order change. Now actually the denominator is, it won't matter because in the end this will be a scalar, but well, in this case in one dimension, but it won't matter. But I'll just include the order change also here. So this will leave me with this and this, which is exactly what we have initially with the original P. And the second one is by doing the square of P. So this will give us with another set of P. And if I just play around with the parentheses, I forgot it's being commutative or some rule, but if I just place the parenthesis here and then this goes out, and it left me with this term right here. So this is also equal to the initial P. So we got the second point covered. Now let's go into point number 3. So let's do the same thing but for n-dimensional matrix. So we have our subspace of A here, and then again we have some vector B that we want to project into those subspace of A, thus we get the projections of P. So we can think of it like, of course, the A have its basis vector of A1 and A2, and again the x hat is the combination of those two basis vectors, so it equal to the projections. So I will rewrite this but in the vector terms, so it will be like this, right? So I have the vector A, vector 2, A2, and then I get this x hat equal P, so this will be the A times x hat equal P. That's it. So this will give me this form, the first one, how to find the projections P. And then so now we define a problem that we want to find x, right? We want to find the solution of x hat. And remember that we still got this, the error term, the vector e. So with the condition of with e perpendicular to the, of course, to this p, okay, and e again is the p minus p, which is in this case is minus ax hat. So let's try to find that. So we have e perpendicular to the p. Now I kind of stuck there because I thought it is perpendicular to p, but it is actually correct that it will be perpendicular to p, but there's also a more correct definition, and actually, you know, solving this will lead to the same result, but I was just following what the Professor Strang did in the lecture, which is perpendicular to the plane A itself, which means to all the vectors in A, including all the combinations of A1 and A2 here as the basis vectors of A. So we can dot the matrix A, the subspace of A, and then this one as well. Now this is actually not, it's actually just, you know, the single vector A times this one, just again the error, and then another one which is the A2 here, and then you just want to dot them. So what does it translate to? It will translate to this one, like A1 transpose, A2 transpose, and then you have the b minus ax here equals 0. Well, equals 0 again because these and these are orthogonal complement. So, and this A transpose because initially the A consists of this A1, A2 vector sitting on its column. So, and then so again this is will be the A transpose, right? Because the A transpose will equal to this one actually, the A1 in the row and A2 in the row instead of the column, the original A. So let me continue this, and then we have this form, and then you may be tempted to do this, but remember there is no such a thing as a division by matrix. So let me put a big cross in it, and what we can do instead is let's do it here. So ATX is equal to ATB, and you know, multiplying by this inverse, so we will get rid of it. So maybe let's put it in a more beautiful way. So we will multiply this by inverse, and also the same thing happen in this side. Then this will be the identity, so x hat is A transpose A inverse A transpose B. And if you recall from what we did in the one dimension, that this is exactly what we got here, but the only difference is that we can do this division by A transpose A because this is only a scalar value. So you can see so far that it's just really as simple as putting the little a into the capital A to what we got here. And following the same directions, we can also have the capital P, which is again, if we derive it from this term right here, let me think about it for a sec. Yep, P is A, and then A transpose A inverse A B, A transpose B, and this will be our matrix P, which is again really similar to what we have initially in the one dimension. Just this term, we change this into a capital A and then we move it upwards, sort of thing. So here I summarize all those three important equations that I will introduce in these lectures. So first is the projection matrix, and this is what you got in the one-dimensional, and this is for the n-dimensional formula, and you got the projections of the B onto the subspace of A. So this is little illustrations just to keep remind you of what's going on geometrically, and this is the solution of x hat. So I think it's just beautiful to see this in comparison, and it's not much different except you just remove the replace the A into the capital A and do some sort of the ordering, because here we are dealing with the matrix and we no longer can divide by a matrix here. A little mistake that I just realized is this B should not be here, so the equation for projection matrix is only this part consists of A. And let's go into the last thing. So we just did the third one, doing the same thing for the n-dimensional, and there's a little notes about this formula right here. So let me rewrite that. And Professor Strang mentioned, what if we say we expand this one right here? So remember, the inverse will change the order as well, and then what you got is this term will be identity, and this is also will be identity. A inverse, A transpose inverse, A transpose. So what happened there? Now we are strictly discussing and we are agreeing that A is not a square full rank matrix. So we always works with this formula that keeps in mind that the A is rectangular, which is m by n, with usually always m equal to n, because we will discuss in the later lecture in the application that so what happens is usually you have a different bunch of measurement in the experiment. So let's say you measuring temperature and there's like A plus B equal to C, x2 C, and blah blah blah, and then you have a lot of things going on here. So you will have a matrix that consists of the A and B, a really long one. So you have a M equation with n unknowns. I'm sorry, this looks really bad, but this spells unknowns. Okay, and usually what happens is that the m is bigger than n, so you cannot find a solution of C immediately, but you need to project the C into some different spaces. So we'll discuss that more in the next lecture, like next note, but just to keep in mind that Professor Shrang also mentioned about this, and that's it for today. Thanks.